Hello everyone. Today we discuss about these robotics and robot kinematics. If any engineers know about the kinematics calculation, that means he is the actually knows the about engineering term, because everyone knows they can understand the uh, theory, but mathematical term, and you have to calculate the how much motion, how much effector we have to set up. There is lots of calculation, but we will discuss few calculation here. Okay, let's start. Kinematic robots and kinematic robots in here in nutshell. We'll know this type of question in this video. And kinematic robots, actually kinematics is relation between joint position. Every joint, this word is important, and in effector position. Joint position, that means which point joint have we have to make. And in effector position, that means if we consider this in effector, how much rotation will be go there. If there are any object, how will go on that object, how catch on that object, how far distance will remain this object. This end effector, this end link is called the end effector. And orientation, that means if we consider this link and this link and that link and this link are actually orientation, how I want to decorate it, or orientation that robotics link or arms. And next is the representation of orientation. When if we look carefully, and here is the some link will ups and down, ups or down, that is we can use there is a prismatic joint. But some joint can rotate, that means rotate. We have to calculate the rotational matrix and Euler angle, and also 4 parameter presentation. We'll focus the rotational matrix here. Okay. Direct kinematics, actually different way we can calculate this kinematics, and homogeneous transformations and Denevit-Hartenberg convention. And kinematic typically manipulator structures. Actually, manipulators, these are the manipulators. If we draw this, this and that, these manipulators, how will shape will provide us? Is it cylindrical? Is it spherical, or is it another any shape? Actually, it's the will depend on the manipulators, how we will manipulate that link. Inverse kinematics, that means in kinematics has two types basically, and the forward dynamics and inverse dynamics. Forward dynamics means if we say in this is place, here is the on rotational and on the prismatic, and here prismatic. Okay, this in inverse matrix, that means generally in forward matrix we are calculate the from initial point to an end effector point, but in inverse matrix or inverse kinematics we have to calculate from end effector to joint, and how much will be joint, how much will be link length, and how much will be rotational, and by this we have to calculate. That means inversely we have to calculate, or reverse we have to calculate. Solution, the 3 link planar arm, and solution the anthropomorphic arm. And solution of a spherical wrist. Okay, gradually we will know. Rigid body. We know the rigid body is that is this secession and the secession is same distance, but their uh, shape can change, but distance will remain same. Okay, if we say one bed, two front and sleeve is there in on time, but few seconds later or few minutes later that friend is on the bed, but the structure has in shape change, but this area is the uh, is in same place, but their structure has been same. And rigid body actually rigid or that can sustain their body or cannot deform easily. That's and rigid body is completely describe the space by that position or orientation, preposition concerning and referring frame. And also this clip, this one is this orientation from this orientation as orthonormal reference where frame x y z, here is a z z x to x prime and x to x prime, all are, but is the shape orientation has been changed, but all are the same axis as the is called the rigid body. Pros pose of rigid body. This is the pose of rigid body formula, and I'm not target for that. Our target is the rotational matrix. This is our target. Rotational matrix, if consider, we always will think in 3D. In 3D position, x naught, y naught, and z naught. Why? Here all are this. This is actually we are considering that here we can consider here y naught, here x naught, and there z naught is depend on actually is not matter, just we have to understand is it which one is the comfortable, which one is the more easy for us, that we have to do. Okay, and here is the rotational matrix. We are considering x1 x0 to x1, y0 to y1, and z0 to z1. When we rotate, when we rotate this x1 go through that, according to that xy will be changed and that will be changed. Always we'll remember that this is 3D. This, if we consider this box, this one is the y. This how much is actually is the, you can say, fat or thick, how much is thick, that is the y, and this x-axis and x-axis, and that one is the how much height is the z-axis, that's indicating here. And always we have to remember this relation for the projection, and x naught, that means initial point x y z, and the next x1 x2 and sorry y1 and z1. Actually we are indicating the previous with respect to x0, y0, and z0. X1 again this array, and if I do clear for more, that it will be helpful for that. Actually this will be this and this, and again for z, this, and for for y and for z is again the same way we have to calculate. I think it's clear to you. And next one is the this one. Yeah, we have to remember this away as same. And yes, projection is very important. And projection, we will call this vector v, because in matrix actually we know the vector has the magnitude and direction, in vector. Also, when we calculate the matrix, we'll get the two values at one time. How? When we give any flash on that y-axis, and that automatically this projection will be there. And if we flash according to there, and we'll get there. Projection, that means shadow, will get in the opposite of light. Okay. Next one is the projection is the same of that. The projection here we can this vector is the projection is same. Actually tan theta, we can denote that, and with both a projection will be this one, and this same calculation we know that. And it is assumed that all these axes have the length a or n. Yeah, ideally we are considering that. And matrix, okay, another one important, the rotational matrix. When we this z1, the rz, that means is rotating according to z-axis, is the universal. You have to remember that when we'll calculate, and when it rotating according to z-axis, this shape will be 1 remain, 0 0, and this cosine minus sine and sine theta, this will be here. And according to x-axis will be that, and y-axis will be this, and just remember this, and z will be that. Remember, it will work for calculation. Yeah, rotating is the real condition. This is the revolute joint, also revolute joint, and the revolute joint. Okay, according to x0, y0 is the initial position. When we'll displace or will work, that will go another coordinate system, and then here we can generate x1 and y1. By this when we'll calculate another way, that means displacement moment, or another portion when we'll do work for another coordinate system, then we'll calculate that time, that coordinate, and that rotational angle. Here is the rotating at a matrix. Before that, we'll know that we have to know the Cartesian. Yes, this one. Okay, This one understanding is very important for that Cartesian manipulators. Here, and this one is the prismatic joint. Where we have denoted here is the Z naught and displacement D naught, D1. Why? Because D is the variable. How much will increase or decrease this arm or limb length? Actually, we don't know. We can denote here is the A1 distance fixed, but D1 is not fixed. D1 plus A1 plus D1. That means D is dependent on that prismatic joint distance, and also like this and that is same, and just change the coordinate system, this from that and Z. And always another thing we have to remember, and for prismatic joint always changeable direction, changeable axis. According to axis will be the Z. But in for rotating, when it will be rotation, then rotation displacement will be the Z axis, and free to take X and Y is actually follow the right hand rule, because is depend on the x-axis. Freely we can denote it, or we can identify the x-axis, but according to x-axis right hand rule, according to right hand rule with respect to x-axis will be y. Also here we can say this one is related rotation Z is same. Also same, all are the same in the degree of freedom. In simple term, ease of joint presents degree of freedom. The robot 3 joint, it has 3 degree of freedom, and the number of degree freedom robot has changed the robot workspace. Joint also we know that allow the person is motion, regular joint that allow the rotational motion. 1 degree of freedom. The system and figure it has 1 degree of freedom. It has on joint. Here it has revolute and workspace circular. 1 degree of freedom. And also in 2 degree of freedom, and 2 degree of freedom has these manipulators and workspace in disk, and 2 degree of freedom. This means we know the in geometry box has this type of pin. The shape is 2 degree freedom, and 3 degree freedoms is that like Z, 3 degree of freedom. It can rotate this, it can rotate this away and that way, and also this 3 degree of freedom. All revolute, 2-dimensional workspace, and the axes are parallel. Thank you for your passion. I try to briefly discuss which is important for actually on robot structure, and don't worry, just I want to touch all the points, try to give the main point to clear that doubt. Otherwise, if you have any query, you can search on Google, and you can watch the video in YouTube. Thank you for that. Thank you for your passion. Thank you. Assalamu alaikum warahmatullahi.